So welcome everybody to my talk. I would like first to thank the organizer for the invitation. Today I will speak about part of my PhD work under the supervision of Matteo Gatti and Lucia Reining. And it was about developing new approximation to the exchange correlation potential from connector theory approach. So let's start from the beginning of the story. As you know, computational materials design is a powerful tool to probe and explore materials, but it involves calculations which have high computational cost, and also we need to redo the calculation for every material. But as you know, all the materials can be seen as systems of interacting particles, and these interactions are the same and they are known. And by repeating these calculations, we are recalculating some pattern many times. And the question is how to avoid this waste, and if we can make part of the calculations once for all. The solution that we propose is to make the calculations in simple systems, which we call models, once for all. Then we give the prescription how to use the model data in real systems. Okay, so using models to approximate is what people often do when they run DFT calculations. Let's see how. According to the Kohn-Sham scheme, a system of interacting particles can be mapped to systems of independent particles living in an effective potentials, which is the Kohn-Sham potentials, and which is the sum of an external Hartree potential and the exchange correlation potential, VXE, which is the unknown part that we need to approximate. So one famous approximation to the VXE is the local density approximation. And let's see how it works. Suppose that we have a real system with such complicated density, and we want to know the VXE. At the same time, we know the VXE in the homogeneous electron gas for many densities. And this is thanks to Quantum Monte Carlo calculations done by Seppele and Alda to calculate the exchange correlation energy of the gas. And so the LDA suggests to see the system locally as homogeneous electron gas with a density equal to the local density of the real system. Then we use this density as an input for VXE of the gas to get the value that approximates the real VXE at this particular point. Then we need to do the same thing for each point. Like that, we see that the homogeneous electron gas is calculated once for all using QMC. And also, in practice, DFT benefits immensely from these calculations. And the question is, can we optimize the use of the model, or can we choose homogeneous density that we plug in the VXE function of the gas, we get the exact VXE. And here comes the idea of the connector. We have a real system in which we want to calculate a quantity. It can be the VXE in this example. And in the model system, which is the homogeneous electron gas in our case, we know this quantity. So we know the VXE if we give an input density. The starting question is, what is my input density that I give to the VXE of the gas to get an exact value for the exact VXE? As you can see here, this density can be different for each point R. And so it's like using different homogeneous electron gas for each point R on the real system. And the direct answer for this question is to invert the equation. This is in principle possible because the VXE of the gas is a monotonic function. And but in practice, the exact VXE is unknown, and it is the quantity that we are looking for. Okay, that's why we need to do an approximation. Well, we can stop here and use this direct approximation of the real VXE, but we want to profit from the model. That's why we do same approximation or an equivalent approximation to the homogeneous electron gas to bring it to the same level of approximation. And then everything is down here. We can invert this equation to get the input density that helps us to choose the value of the VXC of the gas to approximate the real VXC. Okay. Now, this quantity, we call it the connector density. And the question is, how can we test this strategy? In the beginning, I started by this example. So I took a target functional for the exchange correlation energy, which is based on weighted density approximation for the exchange correlation hole. And as you can see, this is a non-local functional. And then I wanted to reproduce its VXC using the connector scheme. The real system, I took a toy example with the periodic density to simulate the case solids. And here we have the target VXC, red line here. And we have the background, the density, shape of the density. So you see here a bump in the region of low density, which is not obvious if we just see the shape of the densities. So we cannot expect this bump in the VXC. Now we need to choose an approximation in order to use the connector. And here I cut the column interaction by a very short distance. And I do the same thing in the model. Once everything is known, I can invert and get my connector density that when I plug in the VXC of the gas, I get an approximation for the real VXC. Let's see first the direct approximation. You see here a very rough approximation, which tends to 0 because I cut the column interaction by a very short range. Now, by using the connector and the same approximation, we see a big improvement comparing to the direct approximation. And by adding the LEA, see that using a very rough approximation and the result of the model through the connector scheme, we find again the LDA. Now, let's use a better approximation. Here, a linear expansion around the fixed density at 0. So we do this in the real system, and we get this is the exchange correlation kernel evaluated at fixed density. We think that is variable. In practice, we have just to take the fractional derivative of the VXC and evaluate it at fixed density. We do the same thing for the gas, and here we have the macroscopic exchange correlation kernel, which is known. Now we invert the equation, and we get the input density for our VXC function to construct a connector approximation for the real VXC. By analyzing this formula, we can see that it is a non-local approximation. And also, for slowly varying density, we can take out the density from the integral, and so we get the LDA, which is correct for this limit. For rapidly varying density, this approximation tends to the mean density approximation, which is for a periodic system. And in the general case, the connector interpolates between these two limits. Okay, let's see the direct linear approximation. We see that it describes well the target in the region of high density. Then it becomes worse when the density is low. By using the connector, you see that the quality of the approximation is maintained here. And also the connector corrects this discrepancy at low densities. Okay, so from this, we can see that we can improve density functions by designing non-local approximations. And also this gave us the help that it works equally for the unknown VXA. Now we come to the question how to use this connector scheme for the true VXA. Well, we can use exactly the same scheme as the weighted density approximation example. And the only difference, I think, here in the exchange correlation kernel, we need to use the true one, which is fortunately available thanks to QMC calculations done by Moroni and his coworkers, and also by the feat, which is done by Corradini and his coworkers. So a hard job is done by other people, and we need to profit from this effort. And here we have an approximation, a general approximation for the true VXA. This connector approximation is implemented in my Python code that solves the Kohn-Sham questions, and so we can get the density. And in order to see the quality or to test the quality of this connector approximation, we need a benchmark. So the benchmark is density calculated using auxiliary field Quantum Monte Carlo by our collaborators, Shui Song and Xuan Chan, and their collaborators. And here in this reference, they show the density of silicon along a triangular route that starts from the center of silicon bond, then through 001 direction to the other one. Then we go through 110 direction to this bond, and then we back to the initial bond. Okay, in the same reference, they show the difference between the QMC densities, the QMC density, and the approximate densities comes from DFT functions. And here we have just the percentage difference. So what I did is to reproduce some of these functionals and add the connector in order to compare. So here the magenta line is the density. The scale is here for the density. And here we have the percentage difference. The gray line is the error bar of QMC. Now we add the LDA. And as you can see here, it has large error on the region of low density. And also it doesn't succeed to describe these wiggles in the middle. The PBE makes an improvement, especially this region. And it gets worse on the atoms. And I think this improvement is thanks to the use of the gradient of the density. By adding PBE0, it's a very accurate description of the target, even on the region with the squiggles. And then we can add the connector, and we have similar performance as the PBE0. And it's even better here in this region, and also in the region of low density and on the atoms. So in order to get an idea about the ranking of these approximations, we can look at the total error. Here we have the total percentage error bar of QMC, 0.26%. The connector reduced the error of the LDA by factor 6. Then we have the other approximations here. So along this route, the best description is given by the connector function. Now we want to make a difficult test for the connector by choosing a system which is far from the model that we use, which is homogeneous. And as you can see here, the density of sodium chloride is mainly localized around the sodium and chlorine atoms. That's why by adding the LDA, you see larger error than the case of silicon. And and it seems that the difficult regions are between the atoms. Okay, here we have the PB0. We see an improvement with respect to the LDA, but still not as accurate as the example of silicon. Then we have the connector, which corrects LDA and make a big improvement this region between the atoms, but yields a larger error on the atoms. And the best description is given by PB. Okay, even for this case, we see that the connector still correcting the LDA. In this case, the error is reduced by factor 2. And I think it's more interesting to compare connector with LDA because the only difference between these two approximations is the input density that we give to the gas. So clearly we see that the connector is optimizing this input density. And so we can conclude from this that the connector VXC leads to a good estimation of the density. It corrects the LDA density since it captures non-local effects. And we see also from the last example that it's more difficult to describe real materials far from the homogeneous electron guide. Also, the connector results can be improved since it's based on a systematic approach. For example, for sodium chloride, we can use a non-homogeneous model, or we can use better approximation to improve the connector result. Now, we come to this question about if we can compare directly the connector VXC with the exact VXC for silicon and the sodium chloride. And in order to do this, we can invert the density. Well, the question of Kohn-Sham inversion is an old question, and it has been explored since 30 years ago. And I think the new thing here that we have very accurate densities for solids, and maybe inverting these new densities can give new insights or confirming old conclusions. Okay, so here we have the algorithm of the inversion. I think it was designed initially for molecules. And the idea of the algorithm is to start with the reference density, which is the QMC in our case, and first guess for the VXC. Then we construct the Hamiltonian, and we calculate the density at this iteration. Then we update the VXC following this formula. Okay, we keep iterating until the base density converge to the reference density. Yes, here I have a check for this algorithm on the LDA density. So I inverted the LDA density to get the LDA VXC. And I show the error of the density, the maximum error on the entire cell here as a function of the iteration number. And we see the convergence is very good. Now I add the inversion, the error of the inversion of QMC. And we see here the error is a little bit different than LDA, it shows kind of plateau here. And if we look at the inverted VXC along the path as a function of the iteration numbers, we see that the algorithm found difficulties to converge on the atoms. And also by doing further iterations, we see that the VXC develops a kind of spikes. And especially in this low density region. These spikes actually they use even the VXC is very spiky. It gives very good density comparing to the QMC density. And I checked also these spikes by changing the algorithm of the inversion with an algorithm used in the IDEA code. And I got actually the same results. And I think these spikes, the source of these spikes is the stochastic noise of the QMC. Because, and this is for two reasons. First, because if we take the LDA and we add a Gaussian noise, so the size of this noise is here in yellow, and you can see it is within the QMC error bar. Okay, and then we do the inversion. We find similar spikes as the spikes we found in the QMC VXC. Yeah, and here the inverted LDA with the Gaussian noise is shown in red, as you can see here. And also when this QMC error bar is very small, as we will see for the case of sodium chloride, these spikes disappear. So that's why I think the source of these spikes, or the reason that the inverted VXC of QMC density is not smooth, this is due to the stochastic noise of QMC. And since all this VXC gives very good density, I choose an iteration where the inverted VXC is smooth. As you can see here, its error is within the error bar of QMC. Now, in order to compare with DFT functionals, we add LDA, PB, and connector. And I think the nice thing here that we see a proportional rule, like the connector, the functional that corrects or that describes well the target is the one that gives the best density. And for silicon, it was the connector. I did the same thing for sodium chloride, and now we have very small stochastic noise from QMC. And so in this case, we see the behavior of the convergence is similar to the one of the LDA. And also, whatever we go with the iterations, we found a smooth potential for the inverted QMC. Comparing to DFT functionals, they are really similar. The only difference here that you can see is on the sodium atom and the chlorine atom. And as you can see here, this is not a really convenient way to compare DFT functionals with inverted VXC from QMC. That's why we suggest to make a scatter plot of the VXC by plotting each point here, which has these coordinates, the density and the VXC. So we move in the real system, and at each point, we read the density and VXC, and we make a plot. Of course, for the LDA, it has a simple function, and it is universal for any system. For the inverted QMC VXC, we see like a principal branch similar to the LDA, but a little bit steeper here. And also we see an extra branch, which is kind of expecting a new environment. So this spread is due to the stochastic noise. Again, if we use a Gaussian noise and we add it to the LDA density and we do the inversion, we see the same spread. Then we have here the PB, which is closer to the QMC here, but expecting an extra branch in the wrong direction. And finally, we have the connector, which expected the extra branch in the right side, and which is the closest one to the QMC for silicon. So I did the same thing for sodium chloride, and here also we can see a different environment. We have main branch for the inverted QMC, which is close to the LDA, and we have an extra branch here, and also here where the density is large. And also, if we see where is this point, see that the point which is closer to the LDA is in an environment which is more gentle than the one which is in the extra branch. So here, this environment is really on the atom, and here we are outside. So using sample algorithm, we obtained an accurate VXC for silicon sodium chloride, and also we see that the connector approximation accurately describes the exact VXC of silicon, and also it's fairly good for sodium chloride. And by looking to this kind of map for VXC, we may suggest to represent the exact VXC in terms of the local density and the factor of the environment. And actually, this factor of environment can depend on the modulus of the gradient of the density, because it gives further information. Because if you see here, for example, this point, which has the same density, they have a different gradient. Maybe this is the reason why they don't belong to the same branch. And if we do the same plot, but with the kinetic energy density, we can easily distinguish between the points that belongs to the main branch, which is closer to the LDA, and the points that are in this extra branch, which characterize the exact VXC. Yeah, since I had many spiky inverted QMC VXC, so I wanted to see the observables. So, for example, the band gap, the Kohn-Sham band gap, and as you can see, even if the inverted VXC is keeping changing, the observable is really stable and converged. And so, even if the VXC is very spiky, it yields the same results for the Kohn-Sham band gap. So this is nice thing. This means that this stochastic noise does not influence the observables. So the same convergence is observed for sodium chloride. And if I can, since I calculated the exact Kohn-Sham band gap here, I wanted to review an old question about if this band gap can be a reasonable estimation of the fundamental gap, and if we can quantify the difference. So here I show an old study from Godby, Schluter, and Sham, where they construct an accurate VXC for silicon. And the way they did it is to use GW to approximate the self-energy. Then we invert the Sham-Schluter equation to get the VXE that corresponds to this accurate approximation for the self-energy. And they found a difference of 0.14 electron volt with respect to the VXE of LDA. In this study, we found almost the same quantity, 0.20 electron volt. And also, we see that PBE for silicon and the connector gives very accurate Kohn-Sham band gap. And here we come to these conclusions. The connector approximations yields an accurate Kohn-Sham band gap. And also, improving the approximation of VXE is not useful to obtain good estimation of the experimental gap, because even the exact Kohn-Sham band gap makes an error of 30% with respect to the experimental gap. And here I come to my conclusion. So in this talk, we see that the connector theory is a general approach for systematic approximation. Also, it can be used to approximate non-local functionals. The connector functional, we construct actually a connector functional that we can use in practice. And we got an accurate estimation of the density of silicon. It was fairly good for sodium chloride. Also, we have from the inversion of Kohn-Sham equation, we have accurate VXE and the Kohn-Sham band gap for silicon and sodium chloride. And also, we investigate the effects of the stochastic QMC noise on the inversion procedure. And thank you for your attention.
Thank you very much, Ayub, for this interesting talk. So it's time for questions. So there's a question already in the chat by Marcus Sida, who says also that it's snowing in Grenoble. There are even a few snowflakes falling in Toulouse today. So Mark, you want to ask the question yourself, or?
Yes, I'll try if you can hear me.
Yeah, we can hear you.
Yes.
So the results look impressive, but I'm not sure that I understand the connector method. So would you be so good as to re-explain that?
Yes. Also, I think the main idea is inspired from the LDA. And as the LDA used the homogeneous electron gas with the local density as an argument of the VXE function. I mean, here we have the VXE function for multi-homogeneous electron gases. And the idea of the connector, for example, in this case, is to optimize the input density that we give to the VXE in order to get an exact approximation for the real VXE.
Okay, so let me stop you right there to make sure that I understand. So
I mean, yeah.
It's like the LDA, but you're actually changing the input density.
Exactly, yeah. Because in principle,
it now has to come somehow from the true density.
From the true density, yeah, it's as LDA. It comes from the true density. Well, it's a self-consistent procedure.
You took the LDA for the VXE, but you changed the density that you put into the LDA formula.
Exactly.
Okay. How did you change the density that you put into the LDA formula?
Yes. To find this density, I start from this exact equation. So at some particular point, our VXE of any real system is a number. And so we can choose input density that gives these numbers for using the VXE of the gas. So we start from this equation, then we cannot invert because we don't know this. Then we have to approximate this equation. I do a linear expression.
Do you think that equation should even be valid?
Which one? The first one?
Yes.
The first one is valid because the VXC of the gas is monotonic function, so it spans all the negative values. So
because nRC is a functional of the density.
yes.
And so what you're trying to do is to construct that functional of the density for nRC.
Exactly.
And how do you do that?
So yeah, if we know the exact functional, we can just invert, but this is useless. So how I do this, I go to something known. So I make a linear expansion of this equation.
You make
And,
what expansion? I did not hear you.
Yeah, linear expansion of the VXC, of the exact VXC and of the VXC of the gas.
Yes.
And so once I do this, I know all the ingredients. So I can invert the equation and get this function. And then I use it here instead of using the local density.
Okay, so that amounts to using a weighted density approximation for the NRC.
Yeah, it's kind of weighted density approximation, but wait here, because yeah, there is a kind of confusion here, because the target functional here comes from weighted density approximation. But for the real system, I use an FXE.
Can you go back to transparencies again? you had a formula. It looked like it was going to answer my question.
Data.
Stop. Okay, go forward one.
One.
Maybe
Just
one more. Go forward one more.
This one?
No. I thought I saw it. And now it's gone.
Is it right now? I mean, this is what I use for any system, because the real FXE, the real kernel, evaluated at fixed density is the non-local kernel of the gas, of the homogeneous reaction gas. And this is available thanks to these calculations. So I have, yeah, I don't use the weighted density approximation as the target function. But if you want to call it weighted density approximation by looking at this formula, it's okay.
No, I see. That looks vaguely like a formula of Sham and Kohn from long ago. So that is expected to work better for solids. Is it then for molecules?
Yes, I think it is valid for both. Yeah, expecting that when you use the homogeneous electron gas for molecules, it can be not perfect. But yeah, I tested it just for solids.
Okay, so that's what Kohn and Sham expected, of course, and they were very surprised to see that it worked for molecules. Fair enough. Thank you.
Thank you. So the two questions, I don't know who was first, so let's do first Rex and then Nicola.
Thank you. Yes, like Mark, I'm trying to get my head around the nature of the connector approximation and how it's being applied in this case. Would it be fair to summarize the connector approximation or the connector method as a way of folding additional exact information about some functional, in this case, VXC of n, into an existing functional approximation, while not losing the benefits of the original approximation? So in this case, if I understand correctly, you're folding information about the exact or the near exact FXC into the LDA.
Exactly. Yes.
Is that fair? Okay.
Yes.
So, I mean, to that extent then, because one is folding in additional exact information, one would normally expect the accuracy to improve. Do you have some way of quantifying whether the results of this particular connector approximation are substantially better than one would expect by folding in the information about FXC in some other way other than the connector method?
Okay, for particular examples, I showed like the example of the weighted density approximation, the toy example, and also I showed the density of silicon and sodium chloride. And through these examples, we see a systematic correction to the LDA, which is the initial functional. And but in general case, yeah, I don't have rigorous proof, but we expect that there is an error cancellation that happens here, and which is the source of the improvement.
What is the error cancellation?
Yeah, I mean by using an equivalent or same approximation in the real system and the model. Maybe the direct approximation is not great, but when we invert this this equation can be similar to this one, and if we have a perfect error cancelling, it will be equivalent to this equation. Yeah, this is just a hand-waving argument, but that's what we expect, and these particular examples confirm this.
Thanks.
Thank you. Next question is from Nicolas.
Yeah, again on this connector here. So first of all, here you do on this slide a linearization.
Yeah.
Is there any good intuitive reason to understand why the connector density is expected to be close to the original density that you put in? Because this is not something trivial for me, that if I put the Kohn-Sham DFT from the, say, from one given iteration, that the connector density that allow me to retrieve the exact Kohn-Sham potential is in fact close to the original density. So is there any simple way, or have you tried to look in fact at how far you get from the density you put in to this connector density? And slightly related to that is usually when you start to introduce the exchange correlation kernel, you sometimes have a self-consistency to the determination of, so here your connector, in the sense that it's kind of this STLS functional. You have from the dissipation fluctuation theorem, you see that your per correlation function you want to approximate is given by the response function. And usually there are in this kind of functional in the exact treatment some self-consistency. I'm wondering if also you have such a self-consistency for each step of your Kohn-Sham. So here when you fix the density, I understand, but as soon as you do a real system, do you also need to do an extra self-consistency for solving the connector density? So I have two questions.
Yeah, just question if yeah, I want to check my understanding. So what do you mean by the connector density, which is close to the exact density? You mean this one or the density
Yes,
that I calculate?
this one.
Yeah, so this one is not. So this one is
on
not.
one previous slide, you do the expansion.
Yes, here I do the expansion. So
which basically assumes that you are close to, it's a Taylor expansion, you assume that you are close to the N0 density, right? So I was wondering if you check this.
Yes, I assume that I am close to the model. the homogeneous electron gas. And it's like taking the homogeneous electron gas system and adding some perturbations. But here it's not the density which is equal to or close to Kohn-Sham density. This is just an input density. And I need this, I need to do self-consistent iterations in order to get the density from the connector. Okay. So in order to get, in practice, in order to get the an equivalent to the Kohn-Sham density or the density, is to take this connector density, put it in the DXA. Of course, we need the real density. We need to start with the first guess, and we do the Kohn-Sham iterations. And now, once we converge, we calculate the density from the Kohn-Sham orbitals. And this is the connector density. So it's not this one.
Okay, thanks.
Yeah, so yes, it's a way how to give an improved input to the VXC of the gas to get an improved VXC. It's not to get directly the density.
Okay.
Thank you. So just to come back to the last question of Nicolas, so there are indeed there's an extra self-consistency loop in this method. Did I understand correctly, or on top of the usual self-consistency?
No, it's just the usual one.
Okay.
So it's just the usual one. You have to start with the first guess for the density here.
Okay.
And you keep doing as you do for LDA.
Okay. And the exchange correlation kernel, so of course it's calculated with QMC once for all, as you say, but then of course there are different interpolations.
Yeah.
Of course, does that make any difference for your functional the results?
Well, I tested just two interpolations. Here I used the Perdue-Zunger interpolation, but I used the one, the Chachi one, and I didn't notice any significant difference.
Perdue-Zunger, they also interpolate the efficacy?
Yes, for
okay.
the efficacy also.
Okay. Are there any other questions? Just one last question. I was wondering, when you compare to these QMC results, so usually, of course, you have that the pseudopotential in DFT is adapted to the exchange correlation potential. And I don't know how these QMC calculations are done. They also are done with a pseudopotential, or does that make the comparison difficult, or is it not an issue?
Yeah, they are done with the pseudopotential. And here to compare with the DFT functionals, we use exactly the same parameters as the same pseudopotential.
Okay.
Yeah.
Okay, last chance if there are other questions. I don't see any, so thank you again, Ayoub, and thanks all for joining.